So hi and welcome everybody to the second part of the lecture. In this lecture we will talk about modulation concept. Why do we use modulation? How do we perform simple modulation? And then talk about filtering and how to do filtering, and after that summarize what kind of effect the channel can cause to your data and how to remove this effect caused by the channel in your data. So modulation of a baseband signal creates replicas at plus minus the modulation frequency. Basically, it shifts your signal that resides on the baseband to higher frequency so that you can transmit it over a long distance. So suppose your signal g of t in time domain given as follows, and the frequency response of this message is given as shown in this figure, and you want to modulate it, you want to transmit this signal basically over a long distance. Can you send this signal around zero through the air or from an antenna? No. Why? Because it's impractical. The signal first in baseband means if it is voice or audio, everybody hears it if you send it. Second, the frequency is so low, so there is no such antenna that can match the lambda. Physical size of antenna will be so big that you cannot design or deal with. To avoid these two problems, you shift it to an appropriate frequency where you will be able to design the antenna and you will be able to share your information only with the intended user. So you multiply it by the carrier frequency, and I tell you draw the spectrum after modulation. You find out that it's a replica of the message itself, but instead of being at zero, it's now at the carrier frequency Fc. And the demodulation, this is after you multiply it by the signal, the carrier cosine W naught of t, you get this. And if you multiply it by a different frequency, you get a different signal. So basically here we multiply it by cosine and here by sine. What's the difference here? Here the amplitude is same and phase is same, but here the amplitude is same, but the phase here, see the phase? Minus pi over 2, pi over 2. Phase here is different. If I tell you, you draw the phase of sine in the frequency domain, you say that in the positive side it's minus pi over 2. In the negative side it's pi over 2. So this is the only difference due to having I in the mathematical formula. So basically this is modulation. Shifting, this is basic modulation in analog communication. For transmission by radio, antenna size is proportional to the wavelength. Low frequency signals, voice or music, must be converted to higher frequencies so that you can transmit them using practical antenna size. Also, to share bandwidth, signals must be modulated by different carrier frequencies, because the frequency you will listen to or you will use to talk over it must be different than the frequency of the other guy, so that you don't interfere with each other and nobody listens the message of the other person. Each one listens only his message. For example, AM radio uses the frequency of 535 to 1605 kilohertz with bandwidth of 10 kilohertz, and this can propagate over very long distances. Yes, why? Because the frequency is so small, lambda is so big, can it travel without too much attenuation. FM radio 88 to 108 megahertz. This is the frequency. This is FC, the carrier. This is this here, W naught. What's the bandwidth? The bandwidth a little bit more. When you have more bandwidth, the quality of your voice or the quality of your message will be better. But when you have higher frequency, the propagation will be a little bit worse than the ones at lower frequencies. So these are used by FM radio and TV bands. Actually, these for ground stations, they are used at different frequencies in North America and different parts of the world. Frequencies can be reused in different geographical areas as well. With digital TV, channel numbers don't correspond to frequencies, in fact, because you have different kind of technology that uses digital modulation and OFDM transmission. So the numbers that you see on the TV, for example, this channel has this number, this channel has no relation with the frequency of the channel. You need to know to go to the configuration button so that you know the frequency of each channel you watch on TV, yes? The number is different than the channel. Bandpass signals. We have bandpass signal and baseband signals. Baseband signals, they are around zero frequency. You cannot send them through the air. And they are wire. Only with wire you can transfer them. While this is baseband, while passband, they are located at higher frequencies. You can transmit them over the air and they are wireless. Yes, if I tell you what's the difference between these two things, you answer me like I told you. You have the base band, which is your original message before modulation. It's around zero frequency. You can transfer it by wire. You cannot send it by wireless. And it's unmodulated. While this is base, while pass band, instead of base pass, you can transfer it wirelessly. It's not around zero, it's around high carrier frequency and can travel through the air. These are the key differences. If GC of T and GS of T are band limited means they are defined over a certain bandwidth. And you have M of T, the modulated message, as GC of T multiplied by cosine plus GS of T multiplied by sine. Then we call this message the modulated band pass or pass band. You can put this before or after, it's the same. Its Fourier transform or spectrum is restricted to, after you multiply and modulate, the frequency, the spectrum, which is the bandwidth of your signal, is defined as follows. Magnitude of f greater than fc minus b, less than fc plus b. So the bandwidth is this minus this, which is equal to 2b. Let me give you example. You saw this example. What's the bandwidth here of this original signal? Let's say from here to here, B. Yes? When you modulate it, the bandwidth here, B, and the bandwidth here, B. What's the total bandwidth? But here around FC, here was around 0. What's the total bandwidth? 2B. This is what it says in math. After modulation, the bandwidth doubles. So you occupy double the bandwidth. This is using simple amplitude modulation. Most signals of interest in communication will be either bandpass, which is RF after modulation, or baseband. Before Ethernet, it can go through wire cables. Now this is modulation. What about filters? A filter is a system that modifies an input, modifies it in a way that's desirable. For example, your input contains 3 different frequencies. You want only one frequency to be transmitted, to travel through the air. An optical filter blocks certain frequencies of light. In communication theory, we usually consider linear filters. Most of the filters we deal with are linear, which are linear time invariant systems. What does linear mean in this case? Linear time invariant means if you have two signals, V1 of t and V2 of t, and make an operation over them, which is L, and let's define this operation as the Fourier transform. So the Fourier transform of the sum of these two signals is equal to the sum of the individual Fourier transforms of these signals. So basically you take each one and you take the Fourier transform for it and then you sum all of them. If you multiply the signal by a factor alpha and take the Fourier transform, you can take alpha out of the Fourier transform. And if you shift it, you can take the Fourier transform of the signal and then take the value at the shift. So these are the properties that apply to a system that's called linear time invariant. Every linear time invariant system is defined by convolution. Any time invariant by convolution, which is given as follows, and we explained it in the previous slides. The signal h of t is called the impulse response because the the operation of delta, yes, suppose you have a system, you don't know its response, you don't know how it behaves, how it acts on your signal. To understand how it behaves to your signals, you just put an input delta and see the response. So the output is basically the response of the system. So that's why we call it impulse response. The response of the system to impulse is this. So if I put unity, a different function, what would be the output? The output will change. But basically you convolve with h of t to find the output. Transfer function is like impulse response, but in the frequency domain. Take the Fourier transform of impulse response, we call it, then becomes transfer function. H of t convolved with V of t is exactly equal to h of f in the frequency domain multiplied by V of f. H of f is called the transfer function. Many systems are best understood in the frequency domain. Many systems, when we look at them in time domain, they are so complex. You cannot understand anything. You cannot make sense of them. But when you go to the frequency domain, things becomes very easy. For example, let's take the example of low pass filter with cutoff frequency B. This is in frequency domain. So you understand that this filter allows the frequency to pass below B. Anything after B stops. It's easy, very easy to understand. But when you go to time domain, it becomes 2B sync 2 by P, T minus TD, becomes like this. How can you understand? It's not easy or not straightforward to understand that it blocks the signal after B from this figure. But here it's very easy to understand it. That's why we move to frequency domain sometimes to understand how things work and to make things easier in terms of calculation and understanding things. So let's give an example. Suppose you have a signal which is cosine. This can be question, for example, in the test. You have a signal cosine 2 by 0.3t plus cosine 2 by 0.8t. Tells you draw this signal in time. You draw it, it's this signal. This is x of t. Why it's like this? Because you have two cosines with different frequencies, summing them together. And h of t is your filter. Sync by t. You draw it in time as well. Sync by t. It's like this. I want you to find the output y of t. What do you do? The output y of t. You tell me y of t is equal to the convolution of x of t and h of t. Yes? Yes, substitute these functions and find the convolution. You will stuck. Why? Because these functions a little bit, when you put them in the convolution integration, becomes difficult a little bit. What do? You go to the frequency domain. Yes, in the frequency domain, what's x of f? This x of t, you have two frequency components. Let me draw them to you. One at 0.3, 0.3, 0.3 but minus. Yes? Minus, and 0.8 minus, and here 0.8 plus. And you have here in the frequency domain one pulse here, one pulse here, one pulse here, one pulse here. This is in frequency domain, easy. What's h of t in the frequency domain? If it is sync in time in frequency, what is it? What's the Fourier inverse of sync? Rect. Rect, sync, sync, rect. You must quickly answer these and memorize them. Draw rect. Rect of this. Sync. It's basically this. Exactly on the axis. Basically, you have here minus, and here you have plus of this. Okay? Now, filter it. Filter it. You have this input signal and you have this system which is filter, kind of filter window, allows certain frequencies to pass, and tell me the result. What's the result of this? Convolution in time domain like this is equal to multiplication in the frequency domain, yes? So basically the output here, when you multiply them with each other, this is x of f in the frequency domain, and this h of f in the frequency domain. The convolution is equal to the multiplication of these. So when you multiply them with each other, and this amplitude is 1 unity, and this becomes half. You know why half? Because you have two sides. When you multiply them with each other, what do you get? This, any value less than 0.0, 0.5 minus 0.5 is 0. So this, when you multiply it with this, what do you get? And when you multiply this minus 0.3 with this, minus 0.3 is within the filter. So it passes. It passes the filter, yes? So what's the result? You get 0. The amplitude is 0.4 at 0.3 minus. And here, what do you get? You get another one here, yes, at 0.3. Do you get this? So this and this, they die. They go away. What do you have? Only you have these two one. So what's this? This is in the frequency domain. Can you take it to time? Yes, it's easy. Just cosine 2 by f. What's f here? 0.3. So basically the output is this function alone. Yes, this function, and you draw it here. Is it easy? Did you understand why we moved to time to frequency domain, and time was complex and frequency was so easy? With figures you were able to solve it. And did you understand how the filter acted and just gave you one frequency, because this frequency is outside of this filter while this is within the filter? So this is how you will solve any question like this. You become filter expert. You know how filters affect your signal. So this, in time domain, the input to your system is this signal, the output is this signal. After all these solutions, I remove now the solution. After all these manipulation, all these things to find out that the output signal is this. Clear? This is what? This is this in math. And this is in time and in frequency, this. 0.3 minus 0.3. Clear? Non-ideal low-pass filter. Non-ideal is the one that has n number of terms, n equal to infinity. You cannot take to infinity. When you have infinity, you have sharp. You have sharp edge like this. But since you cannot design till infinity, you accept to be n equal 1. If it is v equal 1 is like this. When you increase n, you become closer to perpendicular, become closer to ideal filter, but you can never reach ideal filter because you cannot take infinity number of terms. And this is the frequency response in math, and this is in drawing. And it shows you how the increase in n value can make your filter closer to be ideal. And here you have your filter. This is in frequency and this is in time. If you get it in time, because it's close to rect, what's the Fourier transform of rect in time? Sinc. So it's basically sinc. And this is the ideal, and this is better. When n is equal to 4, we call this filter Butterworth filter, and it compares here the differences between the ideal filter and the Butterworth filter. With 4 components, we get practical filter. High pass and band pass filter. This is high pass filter. Why high pass filter? Because it allows frequencies greater than B to pass. And this is band pass filter. Why? Because within a band you allow the frequency to pass. Any frequency, yes, with me, you are with me, any frequency within this band you allow it to pass. Any frequency within this band you allow it to pass. Anything beyond that you reject it, you don't allow it to pass. So if your signal, I give you very complex signal and you get scared of it in the exam, but the signal when you draw it, it's within this domain. Until you filter it, you just neglect it. So don't be scared. You just focus on the filter and see where is your signal is located. Is it within the filter or outside the filter? And if it is high pass filter, cares only about after a certain frequency it passes all the signals, but below that doesn't pass. So this is the mathematical formula of each one, the high pass and the band pass. This is by math, I tell you, by math, and this is by drawing and by talking, explaining by words. In practice, there will be an additional linear phase in the spectral profile corresponding to a delay in time. This makes the filter reliable. But usually we care about the amplitude here because this is the most important thing to see when you are dealing with filtering signals. Another example, when you have x of t, this is example you can try it at home maybe. X of t cosine 2 by 0.3 t plus the same example, the previous one, and you have h of t now. H of t now is not sinc multiplied with cosine. What will happen here? I will give you a hint of how to solve it. Yes? What will happen here to your filter? Sinc by t. What's sinc by t? It's this. In frequency. This is sinc in time. In frequency, rect. I multiply it by cosine 2 by t in time. Cosine in frequency, shift. So basically you get this. At high frequency, you get this one and this one. So you shift it to a higher frequency. What will happen here? Any expectation? Since you go to higher frequency, you shifted your filter to be at high frequency. Which component here has higher frequency? 0.3. So looks like the output of this will be this function, not this function. You need to verify it at home and see if you can solve it, because you might see this in the test, for example. It's just like the previous example, but instead of having the filter on the baseband without cosine 2 pi, here with cosine. And here, different examples when x of t rect 2 over 4. Over 4 means the bandwidth. the duration of the filter for over 4. Whatever on the denominator is basically the duration here. And you have here h of t sync, t, and here the output, or here with one term, here with two terms, here with cosine 2 by t sync t, and all these are examples in wireless communication that we can always refer to and try to understand and deal with. Examples of communication channels. We have the wires that we use to transmit our data over. We have the optical fiber, which causes attenuation of 4 dB per kilometer. We have broadcast TV, 50 kilowatt transmit from the base station so that it can reach your home and you watch the TV channel. Voice telephone line under -9 dBm or 110 microwatt. Walkie-talkie, this is used by police officers. Yes. Bluetooth, the transmit power 20 dBm. It can be 4 dBm, 0 dBm. 0 dBm doesn't mean 0 power. 0 dBm corresponds to 1 milliwatt. Yes, we proved it in one of the lectures. And many other technologies and systems. What's the main problem that we face in communication when we transmit our data? The linear distortion caused by the channel. When you transmit your data, this is your data, x of t. You transmit over the channel acts as a filter, h of t. So it affects your signal. It can cancel some components, it can add some components, so you need to be careful to get y of t. Y of f is equal to h of f multiplied by x of f. Note that h of f attenuates your signal. H of f, you can take the absolute value and the phase shift. And this h of f basically is the big problem we face in wireless communication when we transmit our data. What's your goal as an engineer? Yes? Your goal is to know what's this h of t, understand it, and remove its effect. How do you remove its effect? By division. You divide over it. Channels are subject to impairments. What are these impairments? Nonlinear distortion caused by the front end of your device, like power amplifier, circuits, antenna, matching circuits. Also, random noise, which is coming from electronic devices, from sun, from air, nature. Interference from other transmitters. There are other transmitters. You might be talking, I might be talking. And self-interference, reflections, or multipath. So basically, these are the things. Linear distortion can be compensated by equalization. Basically, you try to estimate the channel, learn the channel, and then equalize by it. And after you equalize by it, you get your signal in the frequency domain. Then you take the inverse Fourier transform, you get it in time domain. If y of t includes noise or interference, which is x of t plus z of t, which is the case, then your noise will be divided by the channel. If your channel is low, then noise over something low, what will happen? It will magnify it. So basically, we call this problem noise enhancement. We usually try to avoid it as much as we can because it's very bad for our system. If our system encounter this problem, then you cannot detect your data successfully. Equalization may accentuate noise, cause noise, may increase it even sometimes. So these are the problems that you will be able to, that we usually try to handle and overcome during designing our communication systems because they are really very problematic, and if you don't deal with them and eliminate them, you cannot have successful communication between two links. So with this, we stop here and we continue next lecture. Thank you very much for your attention and patience with me.